Welcome to Nano Zorro, the podcast of Tech Zorro, presented by Juditova. Engage with your ears about engineering, development and inventions, as well as interviews with experts and hobbyists. You will learn to make better decisions with your designs, programs and manufactures in order to optimize and develop your products and services, or just for fun. You can find the show notes from the episode, the transcription, and much more by entering to techzorro.com/podcast. And now your host, engineer, crafter, and tech enthusiast, Juditova.
If you like this podcast or the blog, and you do want to support the show, go to our site in Patreon to contribute with a monthly donation. You will have early access to its episodes, you will be recognized as a Patreon in the website, among other benefits. There are several tiers available, starting from $3, or if you feel altruist or generous, there are superior tiers. You just have to go to the website techzorro.com/Patreon. In the show notes or description, you will find the link. We will kindly appreciate all contribution. All right then, let's start with today's episode. Hello and welcome to the second episode of the podcast Nano Zorro. I'm your host, Juditova, and today I want to talk a little bit about this new tendency, we could say it this way. You see, the most popular processors on desktop computers use CISC architectures, while mobile and tablets and many other applications use RISC architecture. But whoa, hold on. The fastest supercomputer on Earth is located in Japan. It's called Fugaku and is also based on RISC architecture. So perhaps you don't know these names of the architectures, but you do know the names of the processors. Well, CISC processor usually carries the brand names of Intel Core or Intel Celeron and many others, AMD, Ryzen, and so on. And RISC architecture usually has these brand names such as Qualcomm, Snapdragon, for example, Apple A14 or whatever name it has, Samsung, and many others carry their own name of their processors. So what is this exactly about? Let's take a look at how this approaches, changes and influences how these processors perform according to its architecture. How processors can be classified. This episode will briefly discuss about the differences between two popular mainstream architectures and how they differentiate. RISC and CISC. Both have their respective advantage and shortages with different tasks. It's their approach into handling information that separates and diverges how they construct a microprocessor. So, the instruction set difference. One important difference is the list of instructions. All processors are told what to do by programs or software using an instruction set that it influences the construction of processors and how they handle computing. Today, there are two main commercial instruction sets: CISC or Complex Instruction Set Computing, and RISC or Reduced Instruction Set Computing. Don't confuse RISC with C, which is a topic that we are going to see today, with RISC with an K and end, meaning risico. No, it is a completely different meaning. And well, as I said in the beginning of the episode, you don't know these processors by their architecture's name, but you do know by their commercial names. For example, CISC processors are branded, for example, as Intel Core or AMD Ryzen, for example. And RISC processors are branded as Apple M1 or Qualcomm Snapdragon, and so on. Let's see a brief description of both. What is CISC? Complex computing favors a simple software approach by reducing the length of code and less usage of memory or RAM, which in turn sacrifices the build of a processor, resulting in higher power consumption. What is RISC? Reduced computing favors a simple hardware approach by reducing the clock cycles required for each instruction and the unpredictability of them, which in turn sacrifices the programming simplicity, resulting in higher RAM usage and harder to program software. In the end, don't worry, I'm going to make a table where I sum up all of this that I am talking about. Now, let's see a typical but precise RISC versus CISC example. Multiplying two numbers. To understand how each architecture philosophy differ from each other, it is better to use a simple and short example. If you require a processor to multiply two numbers, which instruction will you have to use? Let's start by defining the parts of the processor required for this example. 1. The main memory is where the variables are located in memory modules, quote-unquote RAM. 2. The registers store data pulled from the memory into a buffer of the processor. And 3. The execution unit is in charge of logic operations to accomplish the math. I will include a graph that is located in the blog so you can see later. But more or less, it is a square representing the RAM, and it has 6 rows and 4 columns. There is only 6 registers to store data, from A to F, which is a rectangle that is located beneath the main memory. And finally, we have the execution unit below the registers. Now, let's say that we have to multiply the numbers from row 1, column 2, and row 5, column 3, and store the result in row 2, column 4. Okay, so how is one architecture is going to do the job and the other one? First, let's see the following feature: how they use RAM. CISC processors are constructed in a way they understand fewer lines of assembly code. The complex instructions are stored in the hardware, and the compiler does not do much effort into translated into assembly. Therefore, less RAM is occupied. Well, here is the command for multiplication. Mult, row 1, column 2, and then a comma, and row 5, column 3. Well, it is actually one line of code. However, in RISC processors, it is much more than one line. So, with RISC processors, on the other hand, focuses on simpler hardware construction, and the lines of code has to be explicitly told what to load and store step by step. Because there is more lines of code, more RAM is required. The compiler also has a harder time to convert higher language code into assembly. There are 4 lines of code. The first is they have to load variable A, which is located in row 1, column 2, load variable B, located in row 5, column 3, then another line which is explicitly the multiplication of variable A and B, and finally store the result in a new variable. Pipelining and out-of-order execution. Since the instruction in RISC complete in equals amount of time, pipelining is achievable and parallel processing helps get things done quicker. CISC is not able to perform this effectively. Out-of-order execution reduces drastically idle time in a processor. It is a complicated topic for one blog post, so I will leave a link in the description, in the notes or description of this episode, so you can learn more about this topic. Instruction length and decoders. Decoders inside the processor are in charge of translating the instruction into operation. RISC have advantage of having a predictable and fixed instruction length. Some architectures of RISC have 4 bytes in length. In CISC, however, it varies from 1 to 15 bytes in length. So, how does this affect the decoders? If they are unable to identify each instruction instantly, they are going to analyze all the incoming code searching for every instruction, or even worse, guessing. This process, of course, penalizes performance. The decoders have an easier task analyzing RISC instructions since they know that every 4 bytes there is a new instruction. This is not the case with CISC. Before instructions have a variable and unpredictable length. Buffers are temporary memory to store the registers used for the operations. Bigger buffer equals to higher out-of-order execution operation capability. In RISC, it is possible to add more decoders easily. For example, the Apple M1 processor. Whereas in CISC, there is a practical limit that this, some experts say, already has been reached. Power and heat. Hardware construction on CISC processors are more complex and requires more transistors to operate. Multiple cycles are required for every operation. In fact, many multiplication on CISC requires more operation than on CISC if they reutilize some of the variables. Now, when we account for millions of operations that occur every second, we begin to see a problem. And a big one. This translates in more power consumption and therefore more heat to dissipate, which are 2 big problems. Summarizing. The advantage of CISC over RISC can be displayed on this table for quick reference. Length of instruction. On CISC, they are fixed and predictable. On CISC, they are variable and unpredictable. Clock cycles. On RISC, they are single clock instruction. On CISC, They are multi-clock instruction. Code length. On RISC, it's longer, and therefore it occupies more storage. On CISC, however, they are shorter. Transistor storage. On RISC, some of these transistors store memory registers. On CISC, some stores complex instructions. Instructions per line of code. On RISC, we only have one. One instruction is executed in one cycle of the oscillator of the processor. However, in CISC, it takes multiple cycles of the processor to do one job, one instruction. RAM usage. On RISC, it is higher per program. On CISC, it's lower per program. Software approach. On RISC, it's easier for machines and harder for humans. On CISC, it's the opposite. It's easier for humans and harder for machines. And hardware approach. On RISC, it's simple. On CISC, it's more complex. Well, that's all for this episode. Today, you have listened about differences about RISC and CISC architecture. Well, we have talked about usage of RAM, pipelining and out-of-order execution, instruction length and decoders, power and heat, and, well, at the end, a table about more specific differences about all that has been talked about the show. I will leave in the description below in the notes all the links and resources that I have used for, more than that, the blog post where it has all the resources I have used to create this episode. One interesting phenomena that I have overcome a few in these years. I used to think that CISC processors are inherently better than RISC. In other words, desktop architecture is better than mobile architecture because, well, complex, it usually meant to me that it has more useful instructions or can deal with more complex variables, matrices, and so on better than mobile chips. But it turns out that it can be even faster at some tasks. This architecture, it is very impressive. As I mentioned earlier in this episode, the supercomputer Fugaku uses RISC architecture and is a supercomputer, the fastest in the world, at least at the time of the recording of this episode. So it kind of rewrites the paradigm of what is a good processor or how a good processor looks like. Now it seems that really less is more. Less heat, less power, less complexity, and less complicated designs and instructions is actually better for not only everyday use, but even desktop computers. It seems that it performs better with RISC architecture. And servers, we couldn't just emphasize how much they are going to save with this, because, well, since they have in a small room much more computers than you have in your home, they are going to suffer much less, let's say, overheating or power consumption in large server farms. So it is interesting to see how this architecture shift can bring much benefit to the computer industry. Well, that's all for this episode, and I have to thank you for staying here until the end. This is Juditova, and I hope that we see each other in the next episode. Bye-bye. I hope you have enjoyed this episode so far and that you have learned something useful for your next craft or project. Before you go, I just need a favor from you. Go to the application where you are hearing this right now and leave us your honest review and a like or a rating from 1 to 5 stars. This way, more people will be able to find this episode and enjoy it as well. It will mean so much. Juditova says goodbye. Until next time.
That's all for this episode. We hope that you found a moment of enlightenment and that you have enhanced your skills or cleared some doubts. For more interviews, tutorials, blueprints, and advice, go to the website techzorro.com/podcast. Juditova expects you in the next episode. Don't forget to subscribe. Happy crafting!